uh, here's what we're looking at, right? We had this. Here's our original problem, original function, and y equals x to the 2/3 minus x squared. And so remember, with our souped up version of the table that we're using now, not only are we going to find the derivatives and include the critical numbers and all that good stuff, we're also going to look at the domain first, and then we're going to find any asymptotes that might exist, and those will be important to us too if we're trying to get an idea what this function's doing. So we asked ourselves, what would the domain be? Are there any places where x would prohibit the function from existing? Like any x's in the bottoms of fractions or inside even roots, and there weren't any, right? Because this ends up being an odd root. I've got a 3 on the bottom. And so we're fine. No restrictions on the domain. It exists everywhere, all real numbers. We took the limit, and we found that the limit of this thing was negative infinity as we approached plus or minus infinity, right? And all we're doing there, remember, is we're looking at the dominant term, the one with the biggest power of x, and just looking to see what happens when we take a limit of that term approaching positive or negative infinity. Well, sometimes it's gonna matter sometimes. If I'm approaching positive infinity, I might get one behavior, and negative infinity the opposite. But in this case we didn't, because the x was being squared, and whether x is approaching positive or negative infinity, the sign of the numbers is irrelevant, because when I square a number, it's always positive. Multiplied by -1 makes it always negative. And so we got negative infinity for the behavior, end behavior on both sides. So as we go really far out in either direction, this thing is tailing down, right? And so then we started in on the stuff that we've had more practice with, the harder stuff, the 3-3 and 3-4 stuff, where we're just going to take derivatives and fill in our table. We differentiated and got this, right? So we differentiated term by term. And then we needed to find the critical numbers of that. And so we started looking. Okay, we factored out, we always want to factor this, because our goal is if we can factor this for a couple of reasons. And let me just kind of reinforce this a little bit. We want to factor this because, first of all, factoring it, especially if I have negative exponents in there, allows me to write this as a fraction, which is really handy. When I write it as a fraction, then when I'm looking for the critical numbers, remember that we want to know where the derivative is undefined or where it equals 0. And all that really amounts to then is where it's undefined, that's an artifact of what we've got on the bottom of the fraction. Whenever the bottom, the denominator is equal to 0, that's going to provide us with the first, or the critical numbers where the first derivative is undefined, right? Keeping in mind that we're not going to worry about any values of x that aren't included in the domain to begin with, though, right? And then we set the top equal to 0, and remember, that's giving us the other type of critical number, where the derivative equals 0, because a fraction equals 0 when its numerator equals 0. And we got some results here. When we set the bottom equal to 0, we factored this thing. We got a negative exponent, which was sent to the bottom. And so when we set the bottom equal to 0, x to the 1/3 equal to 0, and solve, what are the values of x where x to the 1/3 equals 0? 0. And so x equals 0 became a critical number, right? Because that's where the derivative is undefined. We set the top equal to 0, and the top equals 0 when the factor 1 minus x to the 4/3 is equal to 0. And so we solved that. We just isolated x. X to the 4/3 equals 1. And then this is where we had to be just a little bit careful. We had to ask ourselves, for what values of x does x to the 4/3 equal 1? And here's where there's a potential mistake. You have to be a little careful with this. Is it x equals 1 or x equals plus or minus 1? And we decided it was x equals plus or minus 1. And what was the critical detail there that told us we had to include the plus or minus? Good. Okay, good. The even numerator, the fact that this is an even function. And remember, we can distinguish an even function from an even root. And sometimes this stuff gets confusing. We say these in math, this happens a lot. We use the same words to describe slightly different behaviors, but the context is what's really key. It's all important. We would say that an odd root example, you know, the cube root of x is equal to x to the 1/3. So an odd root is going to be the case when something like this. If I have x to the m over n, the odd root occurs when the denominator is odd, right? But an odd or even function occurs when we're looking at the numerator, because that's the power. Think what it means if I say x to the m over n. It means the nth root of x to the m power, and that's what's determining if the function is odd or even, right? Okay. And so when we have that even power, so the numerator is even, that's when we always have to include that plus or minus. Okay. So we got two more critical numbers. We ended up with three. X equals 0, x equals plus or minus 1. And then we can start to build our table. This question only asked for, and this was important too, at least for the test, as far as the test is concerned, only wanted to know about relative extrema and increasing, decreasing intervals. Okay, now why is that probably good news to you when you hear that on a question? It says only first derivative stuff, exactly, right? Second derivative would be required if we were dealing with inflection points or concavity, right? But otherwise, the second derivative is entirely optional, right? It's easy to do, it's probably a good idea. But if it's not, like in this case, if I've got some kind of weird derivatives involving fractional exponents, it's probably not worth the hassle. We just won't do it. So we made our table, and our domain went from negative infinity all the way out to positive infinity. We had an undefined first derivative at 0 and 0 valued first derivatives at -1 and +1. And that's where we left off. I guess we were starting to maybe pick some test points too. We just threw out, you know, -10 to the left of -1, -1/2 between -1 and 0, +1/2 and 10. Okay, so take it from there. What are we gonna? There, we can just see the derivative there. We picked our test points, now what? Okay, yeah, we're gonna plug them in, and just all we care about is the sign, right? Sign of the derivative. So if we take, for example, -10, what are we gonna get? What's the bottom gonna give us? What's the cube root? That's all that is, a 1/3 power is the cube root. The cube root of a negative number is negative, okay? And then on the top, so in fact, how about if we write this out? I'm gonna rewrite that so we can see it a little better. So we got y prime is 2. You guys remember what that is? You know, let's go to the next page. I'm running out of room completely. Remember what was our, we had y equals, do you remember what the original problem was even? Here, I'll do y prime. You probably remember that. Y prime was what? That was 2 times, oh, okay, 1 minus x to the 4/3, okay. Okay, no, do you remember what the original one was? Do you have it written down?
Yeah, y x to the 3x to the 3rd.
Times minus x squared. Okay, good. Okay, so now if we're checking we're checking signs, checking critical numbers here. So, y prime equals, at negative 10, we're getting, it's easier to write it this way. F prime of negative 10 equals negative on the bottom, we got, right? And then at negative 10 on the top, what are we getting? What's going to be the sign of this term right here? How come? Tateo says positive, he's right. Okay, so I have a 4 at the top, it's even, so no matter what number I put in there to the 4th power, it's going to be positive, isn't it? So it's going to make it negative. Good. Okay, so the x to the 4/3 is always going to be positive. Subtracting it's going to make it always negative. All we worry about is the sizing, because we're subtracting from 1. Well, 10's pretty big, isn't it? Negative 10's a pretty big number. So 1 minus a pretty big number is negative. So we get negative over negative, which is positive. Okay, good. And then if we went to negative 1/2, how does that change things? Let's see. F prime of negative 1/2. We're still going to get negative on the bottom, aren't we, in that case? I should probably do that. But on the top now, we're taking 1 minus negative 1 to the 4/3. That's going to be kind of a small number, isn't it? I mean, negative 1/2, right? Agreed?
Yes.
Okay, that's just barely bigger than 1, and so, you know, that's certainly going to be less. Overall, that's going to be less than 1, isn't it? Right? So 1 minus a small number is going to be positive. So that makes it negative, right? And this guy's going to be negative. Good. And then this guy's going to be positive, isn't it? We follow the same logic. Right? Oh, is that right? Hang on. Did you do that right? That's right. Did we get that right? Oh, I think we got those. I'm not sure about those. Let's check those. Let's just make sure. If I put in positive 1/2, let's go through that. What am I going to get if I put in positive 1/2? F of 1/2. On the bottom, we're getting positive. Aha. On the top, we're getting positive. You're right. Because that's 1 minus a small number, right? So that's, aha, that is positive. There we go. Good, good. I saw some looks out there like, are you sure? And good thing we checked. What about F of positive 10? Yeah, that's going to give us positive bottom on the top, negative. So that's going to be negative. Okay. So yeah, so we got it. The last thing maybe we could do then is what's going on at the tails of this thing. I don't know if it even asks for that, but let's just take a quick look. How could I include the end behavior? Remember what we talked about on Friday? How could I put something in here that's going to tell me, it's not an asymptote in this case, but it's still useful. As x approaches negative infinity or positive infinity, we said the function tails down to negative infinity. Where could I include that on the table that would maybe show me that fact, where all the information could be included in that on the table?
Oh, y value.
Good. Y values there? Yeah. Good, good. Okay, because remember, whereas these are traditionally in the table, those are ordered pairs, you can't have an ordered pair that includes the infinities because they're not points. And so the equivalent of an ordered pair would be a limit there, wouldn't it? Right? As we approach negative infinity, x approaches negative infinity, y approaches bad infinity, x approaches negative infinity, right? As we approach positive infinity, x approaches positive infinity, and so we can get our limits in there. Okay? And then, and maybe we'll just skip through this part, but sometimes on the test, or it's when they're asking questions on the homework or the test, they want to know actually points instead of just numbers. Sometimes they ask for numbers. They just want to know the x values where there is a minimum or a maximum, for example. Oh, and what are these things? I guess we should quit maybe just a little bit early. If I draw the little sketch here, which is kind of nice to do, if I draw the little sketch, what is this guy? I'm going from increasing to decreasing smoothly, right? So I've got a horizontal horizontal tangent, and I'm doing that, right? Does that make sense? Okay, same thing here, right? Horizontal tangent, increasing to decreasing. Now what about this guy? How's that going to look when I make my little sketch? Okay, sharp, decreasing to increasing, so like that. Right? Or a VS, whatever you want to make, but just kind of remind yourself that it's a sharp corner. Okay? So the question might ask, there's two different ways the question could be asked. It might just ask for the x values. A lot of times that's all we care about. It might just want to know for what x values are their relative maxima. Then we just get -1 and +1, right? If it actually wants to know the extrema, the points themselves, what do we have left to do? One small. Yeah, just plug it into the function, right? Just figure out what are the y values that go with the x values. So to find out, we just plug them into the original function, right? Okay. All right. Good. Let's take a look. My head just. Oh, I wrote on the wrong spot. I guess I got to erase that. I thought maybe we'd quickly look at. Well, that's really similar to the one we just did. We'll come back to that if we have time. Exactly why I picked that one. Must have been a reason. Well, look at this guy. Here's something new. This doesn't even really honestly come up a lot on the test, but it's going to come up later. It's a good time for us to talk about this. What about this one? Well, let's just do this one the way we normally would, but there's something additional that comes in here that's a little bit tricky, something we can do. Okay, so what are in our revised, souped-up version of the table, before we start doing derivatives, what are we going to do? Domain. Okay, so the domain. Looking at this function, there are no even roots in this function, right? But there is a denominator that includes x's. And so we got to find the places where the denominator is equal to 0, right? Now, what equation are we solving to find that then?
X squared minus 1 equals 0.
Good. And so we're, this is kind of the way, at least the way I think about this, is whenever I'm looking for a domain, I find the part that on the bottom that's going to make it go to 0 potentially. And I just want to ask, when does that equal 0? Because those are the values we have to exclude from the domain. So x cannot equal, in this case, x cannot equal 1, right? X squared, sorry. So what can x not equal then? Plus or minus 1. Yeah. So our domain, a couple ways you could write this. Now, if you're writing this in the Math Excel problems, you have to write it using the interval notation, right? Really, the easiest way to write it would just be that way right there. X does not equal plus or minus 1, because that implies anything else is okay, right? So if there's just a couple places where it doesn't exist, list those, and then we know everything else is okay. How would I write that using interval notation? Good, -infinity to -1, comma, -1 to 1, comma, 1 to infinity, right? It's kind of a pain to do it that way, but that's what it would be. So we got the domain. Now what? What's the next thing? We got the domain. We found out where it's undefined. Plus or minus 1. Okay, and we'll get on to the critical numbers. There's one other thing we were doing before too, though. Remember we kind of wanted to get a scaffolding. Yeah, the limits, exactly. We want to get a scaffolding for the function so we could, I drew you a picture on Friday. I can go back and find that. Something like this. Remember we talked about this, how if you get the limits, they act as kind of a scaffolding. If you can find any asymptotes from the limits, the horizontal and vertical asymptotes, then we really know what the overall behavior of this thing is. We have to just find out the little details. So we want to find out horizontal and vertical asymptotes, or maybe even some other weird kind of hybrid asymptote. Let's see, what do you know? Okay, so we actually have some vertical asymptotes already, don't we? Where are they? 1 and -1. We know those are vertical asymptotes. Why? Okay, because it's not just because the bottom's 0, though. It's because the bottom is 0 and the top is not. They're unique zeros of the denominator. Now, if we got a place where we had zeros of the numerator and denominator simultaneously, those wouldn't be vertical asymptotes, those would be holes, yeah, holes in the function, right? Okay, it's been a while since we talked about that. Was that ringing a bell? Right? Okay, so we got the vertical asymptotes. Those are easy. We already knew how to do those from before. Horizontal asymptotes. Are we going to get them here? We're shaking their heads. That's correct. No, we're not. How come? If I look at that function, why do I know right off the bat that I'm not going to have horizontal asymptotes? It's going to blow up. Good. Because the numerator, the polynomial on the top, is bigger, higher order than the polynomial on the bottom, right? So we know we're going to get this kind of behavior. So what we've done in the past, for example, in the last problem, is we just analyze, we just take limits at positive and negative infinity and just see what the sign of the function is going to be. And we can still do that, but we can do one better here. There's a trick. Notice that in this case, the numerator and denominator, the polynomials, the orders of those differ by exactly 1. The top polynomial is exactly 1 bigger than the bottom polynomial. So not specifically, but generally, just tell me, what's going to happen if I divide out those polynomials, if I actually simplify that quotient? A cubic polynomial divided by a quadratic polynomial is going to result in what? Okay, something linear. And I'm not going to pin you down and say what the something is, because it doesn't have to be a polynomial. In fact, generally speaking, it's not a polynomial. But it's going to be something linear, isn't it? Does that make sense? Okay? Because this is the same thing as saying this quotient, if I were to call the quotient q, and I don't know what that is yet, right? This function, if I called it q, if q equals x cubed over x squared minus 1, then q times x squared minus 1 equals x cubed. And so when I multiply this out, in order for me to get an x cubed there, the overall sign of, or the overall dominant power of q, I'm using kind of made up words, and this is a little bit iffy, but I want you to just get a kind of a qualitative feel for this. It's got to be sort of linear-ish, doesn't it? Does that make sense? Because what times x squared is x cubed? X, right? Okay, that sounds linear, right? If I've got x to the first power. So what would happen then, in this case, if we actually did divide it out? Just, divide the polynomials. And this is a good chance for us to get a little practice doing polynomial division, which I know you're thrilled to hear about, right? Okay, so if we divide this out, first of all, how do I do that? Remember doing polynomial long division? Probably blocked it out. You probably did a lot of this last year, I'm guessing. It's been a while, huh? Yeah. But this is one of those things you hammer on in pre-calculus. So first, let's look at this. Now, I have to use long division here. Normally, I've got 2 options that when I'm dividing polynomials. Kind of the old traditional, normal way, long division, and then in certain cases we can take a shortcut. Synthetic division, yeah. Now, what's the rule? When can I use synthetic division? When the denominator is? Okay, well, it's when it's linear, right? Okay, so when the denominator is linear, so it's just like x plus something or x minus something. I think I was hearing that, but I just didn't get it for sure. Then I can use that shortcut of synthetic division. Okay, but in this case, I've got x squared minus 1 there, right? And so it's not linear, and so we're stuck doing long division, which is worth having a look at. So how do I do this?
1 times x squared equals x to the third.
Okay, good. We're always just going to look at the quotients of the leading terms, right? So we're going to take the leading term outside and divide it into the leading term inside. Now, there's only one term in the numerator, but what if there were a whole bunch? There could be, right? I just want to know how many times does the dominant term outside divide into the dominant term inside, aka x squared times what is x cubed. I could always just write it out, by the way. If I want to know what goes there, I could just divide the first two terms, x cubed divided by x squared. It's x, isn't it? To me, I always ask myself, I just say, what times that is that? That's an easier way to think of it for me, but maybe it's not for you. So, x. Now what?
Multiply x by -1.
Okay, I'm gonna multiply the x all the way through this whole polynomial. Now, if this is kind of a weak example in a way because there's only that one term in the top. I'm gonna erase these in a second, but just pretend, just for this moment here, pretend that the top was really like x cubed minus 2x squared plus x minus 7, something like that. It's not, but what if it were? When I distribute this x through, what do I always have to do? I get x cubed, right? And then minus x.
Put a 0.
Okay, I gotta line it up with the x column. And so what you wanna be careful to do, and we'll do plenty more of this year, I promise you. But just to kind of I'm gonna give you just a short example now, we'll come back to it later. But when you're doing, the moral of this short story I'm telling you here in pink, is that when you're dividing polynomials, you always want to preserve a column for every power of x, because you never know in this long process of dividing and subtracting, getting a new polynomial and dividing and subtracting, you never know when you're going to need to use one of these columns, one of these powers of x. So you have to always make sure you leave room for these, right? If you're missing one. In this case, it didn't really matter so much, but so we'd end up with then, if I distribute that x, I get x cubed minus x. Everybody agree? Okay, and now if I subtract the whole thing, and I urge you to write it this way, I urge you to put a negative out front and always put that in parentheses, because you're actually subtracting each term. And then when you go through the process of doing this, you get into a pattern. When you're actually doing the subtraction, you always go from here to there to the term. So x cubed minus x cubed cancels. They have to, of course, right? We chose it that way. There's really a plus 0x up there, isn't there? 0x minus negative x is what? Positive x. Okay? And we start over. So that's our new polynomial is x. But how many times does x squared divide into x? Doesn't, does it? Right? Okay, so then this becomes our remainder. And so what is this equal to? So this quotient then, if I rewrite it, let me just grab it and copy it here. So what's that equal to? What's the result of our division there then? We got the answer x plus okay, good. My remainder is what remains in the numerator. That's what remainder means. So I get x plus x over x squared minus 1, right? You see that? Okay, so those are literally equal to each other. The original function, when divided out, is equal to this. What's the advantage of that? When I'm taking the limit. Well, maybe it's not obvious what the advantage is, but look what happens here. If I take the limit of this thing, if I take the limit of f of x as x approaches plus or minus infinity, I get the limit of this stuff, right? What's going to happen to this term? What's going to happen to this where I've got a more powerful denominator than numerator? Okay, that term is going to go to 0, isn't it? Right? That limit goes to 0. And this is just one of the cases that we looked at in 3.5. This is just a rational function where the bottom polynomial is higher order than the top. And so this thing goes to 0, and all we're left with is the limit is just the limit of x as x goes to plus or minus infinity. Now, sure, that equals plus infinity or minus infinity, but more importantly here, it actually has a shape, right? In the limit, this function looks like the simple function y equals x. And so we call that a slant asymptote, right? In the limit that x approaches plus or minus infinity, the function looks like y equals x. The other term went to 0. And so when I draw the asymptotes on this thing, then look what we get. Okay, we had vertical asymptotes at plus and minus 1. All right, so there and there. And then we had this slant asymptote at y equals x. And so in here, it's probably not going to matter. In here, that slant asymptote is meaningless, right? Because who knows what the function's going to do in here. But out here at the tails, it's going to have to stick to that guy. And so if I look at the overall behavior, there's really only a couple big options, big scale options on the right. It's either going to do something like, I need a new color, what am I doing? How about green? It's either going to do something kind of like that, or maybe it'll do something like that. Having that slant asymptote is useful. Over here, the opposite. Like that, or like that, right? Does that make sense? Okay. And honestly, the rest of this problem is pretty boring. It's the same kind of stuff we've been doing. But I just wanted to show you that slant asymptote. Okay. When do we look for that? What's the fingerprint of a slant asymptote? If we go back and look at the original function. Okay, good. So we've got a rational function, so a ratio of polynomials, right, which we do, where the order of the numerator is exactly 1 higher than the order of the denominator. And then we know when we divide it out, we're going to get something like this going on, right? I'm going to end up essentially getting, the limit is going to be a linear equation, y equals mx plus b. And in this case, b just happened to be 0, but it didn't have to be. I could have gotten something like the limit of f of x equals the limit of 3x plus 5 plus something that's going to disappear, right? And then that would have been a slightly different. Then the equation of the slant asymptote would have just been y equals 3x plus 5 instead of y equals x. Okay? And from there, we would just do the problem the very same that we always do. Now we would just take derivatives, set them equal to 0. So we finish that one up. That's probably all we have time for. Let's just finish that one up, and then we'll call it good. I bet you then you guys are probably ready to maybe start finishing up the work and taking the test. So let me go to the next page. How about, whoops. And I think we said x cannot equal plus or minus 1 is our domain. And we might as well include, we had slant asymptote y equals x. So now let's just do our derivatives. What's f prime? X squared minus 1 times 3x squared minus divided by, oh, I know what else I was going to do. Oh, slow. Divided by, that's a pretty good line, isn't it? Okay, and so let's see if we can just quickly, what's that going to simplify to if we just do this in your head? What are we going to get here? This is good practice doing this, man. It really is. x to the fourth. Okay, what about anything else? If I distribute that 3x squared, okay, good, minus 3x squared on the top. Does everybody see that? Okay, over x squared minus 1 squared. Okay, there's our first derivative. Now, I want to at least get through this derivative. I want you to see something here. So let's find the critical numbers, right? To find critical numbers, of course, we look where the derivative is undefined or equal to 0. So f prime is undefined when what? One more pretty important thing here I want you to see. When's the bottom equal to 0? Plus or minus 1, okay. Right, because it's when x squared minus 1 equals 0, when x squared equals 1. Are those critical numbers? No, they're not. You're right. How come? Paisley, how come those aren't critical numbers? It's already undefined. Good. Because they're not in the domain. I thought I saw you going, maybe I was reading into it.
No, I didn't.
I thought you did. You had a hunch that's what it was. I know you did. So those aren't critical numbers because look, the function isn't defined there. Those are vertical asymptotes, right? And so those are different than vertical asymptotes supersede critical numbers. You can't have a critical number where the function doesn't even exist, right? And what the derivative has really done, one way of kind of describing this is, remember, the derivative, if I started off with an x squared minus 1 to the 1, by the quotient rule, we can already see that the base, x squared minus 1, we're going to inherit that base in each successive derivative, aren't we? We're going to just get that same base in the bottom to increasing powers. And so we inherit all that asymptotic behavior from that first derivative. It just keeps going. So those are not critical numbers though, right? Not critical numbers. Where would we have critical numbers? I mean, you have to maybe solve the equation, but zeros. Okay, so f prime equals 0 when the numerator equals 0. X to the fourth minus 3x squared equals 0. Now, how are we going to solve that? Good. Okay, and that's something another thing I want to just reinforce here. Sometimes people are tempted to solve this in this way, but this would be a mistake. This is not okay. If I were to add 3x squared to the other side, so I get x to the fourth. You see what's going to happen here probably. X to the fourth equals 3x squared, and then people are tempted to cancel an x squared. Right? If I divided both sides by x squared, I'd end up getting x squared equals 3. That is wrong. And here's the huge red flag that I want you to see. This should feel very, very unnatural and just wrong. Dividing variables. You can't divide both sides of an equation by a variable. Remember that. Tattoo that into your brains. Dividing both sides of an equation by a variable is equivalent to eliminating solutions. You can never do that. You can divide both sides of an equation by a constant freely. That's not a problem at all. But you can't do this. So we must factor this instead, right? So we factor out an x squared, and then we're just left with 4x. Oh, I'm sorry. Gosh, I'm trying to hustle here, and I'm making mistakes. And we're left with x squared times x squared minus 3, right? And so if I, by the zero product property, then don't I just get either x equals 0 or x equals plus or minus root 3 if I just square root both sides? Does that make sense? So there are my critical numbers. And then we could test points around those, right? Okay, good job. All right.